So in today's lesson, we're going to talk about some trends in the periodic table. Yesterday, we reviewed some of the trends we learned in grade 10 science with regards to the number of valence electrons and ionic charge relative to an element's grouping on the periodic table. And today we're going to just talk about a few more trends that can be useful in interpreting what might be going on in certain chemical interactions. So the first topic I want to talk about is atomic radius. So I'm going to make a statement, and then I want you to think about why that statement makes sense. So the statement is, as you move down a group, atomic radius increases. So I want you to pause the video for a second and think about why that might be. Okay, and so what I'm hoping you immediately went to is that as we move down a group, we're adding not only simply electrons and protons because the atomic number is increasing, but we're also adding extra energy levels. Those extra electrons need to occupy energy levels. So as we move down a group, we're going to be adding more and more electrons that need to occupy additional energy levels. Let me switch to a different screen and then because I have a diagram of this. So for instance, if I were considering lithium, sodium, and potassium, looking at them on the periodic table, their lithium, sodium, and potassium are directly beneath each other. We know that they all will have the same number of valence electrons, but we've had to add an extra energy level. So that extra energy level is going to make the distance from the center of the nucleus to that valence energy level, to that valence electron, larger as we move down. Okay, so take a minute. Let's just review this. As atomic number increases, more electrons are present, which need to be placed in additional energy levels. This makes the distance from the center of the nucleus to the valence energy level greater. Now, hopefully that makes sense, and that we can go from there and talk about some more trends. I was hoping that that one would be fairly familiar and that would make sense easily to you. Now, let's go back to this periodic table. Okay, I want you to think about and pause the video and think about, well, what happens to atomic radius as we, instead of moving down a group, we move across the period? In other words, what would we say about the size of a lithium atom versus the size of a fluorine atom, as an example? So many people get this wrong, in fact, and so I'm going to switch to a different screen and we're going to talk about it. Okay, so here is the big reveal. As you move across a period from left to right, the atomic radius decreases. Now, you either got that right or you didn't. And if you didn't get it right, I want you to stop now and think about why it is that atomic radius might decrease as you go across a period from left to right. Okay, let's talk about it. So what I've pulled out are three elements that are in the same period, just right next to each other. So nitrogen, oxygen, and fluorine, right next to each other. And so what we need to remember is, yes, and many students will often say, all right, well, since they have, the same number of orbits or energy levels, they must have the same atomic radius. And although that is a reasonable assumption, what we tend to forget about is that as we're moving across a period, we're also adding protons to that nucleus. So that nucleus is becoming increasingly more positive, which is going to draw in those negative electrons towards its center, right? And so the effect of adding protons to the nucleus as you move from left to right across the periodic table is drawing those electrons in and therefore making the atomic radius less. Okay, so as you move across a period, electrons are filling the same energy level, which you would think would keep the size of nitrogen and fluorine the same, but we're also adding protons to the nucleus, which is going to make that nucleus really strong and attractive to the electrons. That's going to pull them in closer. All right, let's look at the next trend. Okay, and so the next term that I want to introduce is ionization energy. And so in the word ionization, we have the word ion. And you'll remember that an ion is simply an atom with a charge. So an atom that's either lost or gained electrons. So in the case of ionization energy, what we're really talking about is the energy that's required to remove an electron. So here we have potassium, and potassium is an alkali metal, so it's going to have one valence electron. So instead of drawing out the whole Bohr-Rutherford diagram, we simply have this little dot there representing its one valence electron. And so when we think about potassium, it's going to want to lose that one electron so that the shell beneath is full, right? So we're obeying the octet rule. And so when we talk about ionization energy, we're talking about the energy that we need to put in to pull that one electron off, okay, of potassium in this case, right? And so that's going to create a positive potassium ion, and then we're going to have a free electron. So again, ionization energy we define as the energy required to remove an electron from its valence energy level. Okay, and so let's talk about what we would anticipate being the trend if we were moving down a group. Okay, so you should have your periodic table kind of front and center here to help you understand the trends. So here I've positioned lithium and sodium. And lithium and sodium are just one beneath each other in that alkali metal group, right? And so think about, well, what would you expect the relative amount of energy to be to remove the one electron from lithium versus sodium, right? So which one would require more energy? Well, when I think about each of these, I'm thinking about the fact that they both have one electron to lose. So they both want to lose that electron. But which one is going to require, which of these elements are we going to need to input more energy to remove that electron? Well, I'm thinking about the fact that both of these elements have that positive nucleus, right? That positive nucleus. And so it's all about proximity. So this one valence electron here is pretty close, pretty proximal to the pull of the nucleus, whereas sodium has its electron pretty far away from the pull of the nucleus. Sort of think of it like magnets. If you had two magnets that were closer together, they're of course of opposite charge, and so the closer those magnets are together, the more you feel that pull. So it's the similar idea for lithium and sodium here. And so, lithium is going to hold on to that electron a little bit more closely, and it's going to require a little bit more ionization energy to remove it. Another thing that comes up is the idea that these inner electrons here, they're going to act as a shield, right? They're going to kind of shield the nucleus from this one valence electron. So that's called a shielding effect. And so it means that the nucleus is going to have a weaker hold on that one electron in sodium relative to lithium. So hopefully that makes sense. Let's write a little bit down. Okay, so as you move down, I'm going to move this up a little bit. There we go. As you move down a group, ionization energy is going to decrease. It's going to take less energy to remove an electron from remove an electron from an atom when that electron is further away from the pull of the nucleus. Okay, and so those inner electrons are also going to act as a bit of a shield, shielding that positive pull from that outer electron. Okay, let's look at what I want you to think about now is, well, what is going to be the trend as we move across a period? Let's go back to the periodic table for a second here. And so now what I've pulled for you is lithium versus oxygen. Okay, we're going to compare lithium versus oxygen. So we're moving from left to right across a period, right? And we talked about atomic radius and how atomic radius is going to decrease from left to right. So oxygen is going to be smaller than lithium. So I want you to think about how atomic radius might impact ionization energy, right? So remember, ionization energy is the energy required to remove an electron. And so there are a couple of things that I'm hoping that you're thinking about here. And one of them is the fact that lithium really wants to lose that electron, and oxygen has 6 valence electrons. If anything, it would want to gain electrons. So lithium, because it becomes vastly more stable by losing its outer electron, it's going to not require a whole lot of energy to make that happen. Whereas oxygen, it is. And there's another factor we need to think about. We need to think about the fact that lithium, with an atomic number of 3, has 3 protons holding that 1 valence electron in, whereas oxygen has 8 protons holding its 1 valence electron in. Well, it has multiple valence electrons, but we're talking about removing 1. So oxygen is going to have a much greater hold on its electrons in comparison to lithium because of that nuclear force, that stronger nuclear force. Okay, so let's write a little bit down. Okay, so as we're moving across a period, our ionization energy is going to increase. It's going to take more energy to remove an electron because the valence electrons are becoming closer to the pull of the nucleus, right? Because atomic radius is smaller. Okay, so nuclear pull is going to be greater and greater because of the atomic radius being smaller. And the reason the atomic radius is smaller is because of that stronger pull, the greater number of protons pulling all of those electrons in. So it's going to take a lot more energy to remove an electron from oxygen compared to lithium. And the same holds true as you move from left to right across a period. Okay, next trend. Okay, so electron affinity. And so I want us to remember that chlorine actually has 7 valence electrons around it. Okay, so its position on the periodic table is such that it has 7 valence electrons. And so it really wants to grab onto an extra electron to fill its valence shell. And so when an atom gains an electron and becomes more stable, we're going to see some energy being released. It's kind of like this chlorine atom with its 7 valence electrons, its unfilled shell, is really, really unstable and stressed. And so by giving it what it needs at the time, that's going to reduce its stress level, and it's going to release the excess energy that it was kind of needing to keep itself together before. So the definition for electron affinity is the energy that is typically we're talking about released or absorbed, and we'll talk more about that later, when an electron is added. So regardless of whether energy is released or absorbed, we're talking about adding an electron. Okay? Ionization energy refers to removing an electron. Electron affinity refers to adding an electron. And so let's think about these two elements, fluorine and chlorine, that are one beneath each other on the periodic table. So fluorine is a halogen and chlorine is right below it in the halogen group. And so I want us to think about, well, which of these elements would want that electron more, right? And in getting what it needs is going to release more energy. Well, I'm hoping that if you've been made sense of what we've been doing so far, you'll understand that it's all about atomic radius. So the radius of fluorine's radius is a lot smaller because it has fewer electrons. So its valence electrons are much closer to the pull of the nucleus. And so that positive nucleus is going to be able to better pull in electrons in comparison to chlorine. Chlorine also has some shielding effect going on here because of those inner shells that will prevent it from being able to grab an electron as easily and therefore release as much energy as fluorine would by grabbing an electron. Okay, so let's write a little bit of that down. Okay, so the smaller an atom, the greater its electron affinity. Valence electrons are going to be closer to the nucleus, making it far easier for the atom to grab onto an electron. So that's the first piece of this. And I also want to talk about this whole business of released or versus absorbed. Okay, so some atoms are not going to want to have an electron added to them. In fact, they're going to reject that. And so in order to add an electron, we're going to have to use a whole lot of energy to push that electron where it doesn't really want to be. So let's talk more about that. So we would say that positive values for electron affinity indicate that we're putting in energy. And the way that you can think about is that, a plus means you're adding energy. Negative values for electron affinity mean that you have a release of energy. right? And so you can think about the system is going to release energy, it's going to lose energy, its energy is going to go down. Okay, so I want you to think about an element that you would expect to have a negative electron affinity, and an element you would expect to have a positive electron affinity. And you can pause the video and think about that now. Okay, and so a negative electron affinity would be an element that is going to be releasing energy. In other words, it wants to gain an electron. So we would say that something like fluorine would be a good example of that, chlorine, and so on. You know, those elements have 7 valence electrons. They're going to become more stable by gaining electrons. Now, positive electron affinity, I would say, well, an element maybe like sodium, for instance, that has 1 valence electron, doesn't really want to gain another electron. It's pretty close to being stable. If it loses an electron, it's going to become stable. Sodium does not want to gain an electron, and so adding an electron to its valence shell would actually require energy. So we would say it's a positive electron affinity. Okay, so I think that's where I want to stop with definitions today. We'll carry on with trends tomorrow when classes resume. What I want you to do is just make sure that you spend some time today sorting out the difference between ionization energy and electron affinity so that you're ready to do some work tomorrow. And we'll see you soon.